Hello, and welcome to the section on oxidation reduction reactions. We're going to have two sections dealing with oxidation reduction reactions. This is just a little kind of overview of some things we're going to start to talk about. First, we need to talk about oxidation states, and we'll do a little review on what oxidation is and reduction. What we call it when something gains electrons, when it loses an electrons. What is an oxidation reduction reaction? Oftentimes it's called a redox reaction. We're going to look at reducing agents and oxidizing agents and go a little bit more in depth than we have in the past when we talk about oxidation reduction reactions. So let's get started. So let's take a look at this reaction. We have two molecules of solid sodium plus one molecule of chlorine gas, it's diatomic chlorine, and that is producing 2 molecules of sodium chloride. This is an oxidation reduction reaction. Why? Remember, because electrons are transferred. We know that because we have elemental atoms on this side, and we have a molecule where those atoms are entering into a bond together, and it's an ionic bond. We have a metal and a nonmetal, and electrons are being transferred. When we talk about electron transfer, we refer to oxidation as the loss of one or more electrons. Reduction, by definition, is the gain of one or more electrons. So, this is a little diagram showing that. If we have something right here, an atom or a molecule that is donating an electron, that is being oxidized. It is going from having an electron to not having an electron. This is the oxidation part of the reaction. It's losing the electron. That electron is going to this atom or molecule in the reaction. This is our electron acceptor. It is going from not having one to having an electron. We say it is reduced. And you'll just need to sort of get that firm in your mind. Reduction doesn't mean it's being reduced by losing electrons. It's gaining an electron. So you could think of it's being reduced because it is gaining negative charge. So it gains those electrons. And you'll need to remember those, memorize the difference between them, because we're going to be using those a lot when we talk about redox reactions. Here's just another way to look at it. If we have compound A and it loses 2 electrons and becomes compound A without some electrons, it has lost electrons. We say that A is oxidized. It loses electrons. Likewise, here's compound B. It is gaining electrons, so we say that B is reduced because it gains electrons. Another term, and we're going to talk about this a little bit later as well, because A is oxidized, A is also called a reducing agent because it facilitates the reduction of the other compound. Likewise, B is reduced because it gains electrons, but it facilitates the oxidation of the other compound. So we call B an oxidizing agent. So how do we know which element is oxidized and which one is reduced? And I already see a little typo here. This should say oxygen. Sorry about that. Let's look at this example. Here we have a reaction. We have elemental magnesium and oxygen, and they are being synthesized into magnesium oxide. So let's look at what kind of charges, electrical charges, are occurring in each of these situations. Here we know magnesium, solid magnesium. What charge is on those 2 magnesium atoms? Well, if there was a charge, it would be indicated because there would be a plus or a minus, right? And magnesium, we know when it's ionic, tends to be +2, Well, in this case, magnesium has no charge. It's zero. Oxygen, the same thing, no charge. It's bonded to another oxygen. They're neutral. These are neutral atoms. When the two bond, magnesium is going to be +2 and oxygen is -2. We look on the periodic table, oxygen gains 2 electrons, magnesium loses 2 electrons. So since magnesium loses 2 electrons, magnesium is oxidized, right? Because it loses electrons. Oxygen, on the other hand, is reduced because oxygen gains electrons. Now, what I have just described to you, we have a term for. It's called oxidation state. Sometimes it's called oxidation number, but the oxidation state is simply the value of a charge that is assigned to each different atom. So if there are multiple atoms represented in a compound, the oxidation state would apply to each individual different atom. It would be the charge that each of those possess. So for binary ionic compounds, it's really easy. The oxidation states are simply the charges of the ions. For example, sodium plus. The oxidation state is +1. The chloride ion, it's just -1. Magnesium 2+. Oxidation state is +2. For oxygen, for an oxide ion, it's 2-, it's -2 for the oxidation state. Now, what about in the case where we have covalent bonding going on, such as water? Although it is not completely accurate, oxygen does not take the electrons. It is the more electronegative atom. It's slightly negative and the hydrogens are slightly positive. For the purposes of assigning an oxidation state, chemists generally go ahead and assume that oxygen takes those electrons and hydrogen loses them. So in a case where you have a covalent bond occurring, chemists will just assign an oxidation state as though it really is a more ionic bond. So we end up with oxygen being -2 and hydrogen being a +1. Okay, here we have our official rules for assigning oxidation states. So hopefully this will cover every different permutation of problem you might encounter. You can assign oxidation states for all different situations. First rule, an element has an oxidation state of 0. So in your chemical equation, when you come across a pure element, sodium metal, for example, you already know it has an oxidation state of 0. There is no charge on that. Rule number 2, this is kind of a typo, should be monatomic with an A. A charge on a monatomic ion. For example, there's just one atom and it's an ion, like chloride ion. The oxidation state is the charge. So the oxidation state for that ion is -1. Rule number 3, oxygen gets an oxidation state of -2. An exception would only be in the case of a peroxide. Here's hydrogen peroxide where we have H2O2. Under all other circumstances, oxygen will be assigned an oxidation state of -2. In carbon monoxide, oxygen has an oxidation state of -2. In this peroxide, oxygen would have a oxidation state of -1. Rule number 4, in covalent compounds with nonmetals, such as the hydrofluoric acid here, we have 2 nonmetals, it's a covalent compound, hydrogen is assigned an oxidation state of +1. Rule number 5, in binary compounds, the element with the greatest electronegativity is given the negative oxidation state. So in this example, the most electronegative element is fluorine. And so we give it the negative oxidation state, would be -1. Sodium then would have the positive one. For a neutral compound, now these last two are kind of similar, but for a neutral compound, the sum of the oxidation states is going to be 0. So when we start assigning oxidation states, let's look at this example right here. Let's look back. We have an oxygen here, don't we? That's our rule number 3. Oxygen is assigned an oxidation state of -2. Oops, -2 right there for our oxygen. Sodium is going to be given the oxidation state of +1. Okay, now how do we assign the oxidation state for carbon? Well, the sum of all of these has to be 0 because this compound is neutral. We know 2 times 3 is 6, so we have -6 there. Let's just write that down, -6. We have 2 times 1 here. We have a total charge of +2. So that's total charge so far of -4. So carbon is going to have to counteract that. Carbon is going to have a -4 oxidation state assigned to it. You can read that very well. And that makes the entire compound neutral. And the very last rule for ions, the sum of the oxidation states needs to equal the overall charge. So it's kind of similar to this. The ammonium ion, NH4, let's go back and look at our rules. Hydrogen is going to be a +1 charge. So let's write +1 for the hydrogen. And there are 4 of them, so that's +4. We know that nitrogen has to have an oxidation state that is going to give us a total value of +1. So nitrogen is going to have to be -3 because 4 minus 3 is going to be +1. So in this case, nitrogen is a -3 charge. And that gives us the total overall charge of this ion of +1. All right, let's do some examples together here. If you have those rules written down, please refer to the rules as we work through these. First example, phosphorus. It's just elemental. Its oxidation state is 0. We're going to assign oxidation states to each of these is what we're doing. Number 2, there's a fluoride ion. Remember, it's just the charge of that ion. It's a monatomic ion, -1. Here we have a typo. Should say SO2 with the 2 in subscript. For this example, we're going to look at sulfur, and let's see how to write this here. We're going to look at sulfur and oxygen separately. Now remember, oxygen is going to be a -2, so let's put a little comma there. Oxygen is going to be -2 for its oxidation state, and there are 2 of them. That means that's a total of -4. In order for that neutral compound to remain neutral, sulfur must have an oxidation state of +4. For hydrogen peroxide, we have hydrogen and we have oxygen. And remember, in a peroxide, oxygen has a -1 electronegative value. Hydrogen gets a +1 value, and that makes that a neutral compound as well. Let's look at magnesium bromide right here. This is an ionic compound, and we are assigning oxidation states. Magnesium is +2, the bromide is -1, and just checking, it makes a neutral compound because there are 2 bromides, so 2 minus 2 is 0. Number 5, here we have ammonium chloride, and in this case, we're going to use several rules. There's an ionic bond between the ammonium ion and the chloride ion. So if we look at these separately, we look at the ammonium and the chloride. We know that chloride is going to have a -1 oxidation state. What about the ammonium? We know the overall charge on the ammonium is +1. So the oxidation states for nitrogen and for hydrogens needs to equal +1. We know the oxidation state for hydrogen is +1 from our rules. And then we know the oxidation state for nitrogen is going to be -3 because we need the ammonium ion overall charge to be a +1. And there are 4 hydrogens with each a +1 charge. Now let's look at the very last example, a nitrate ion. We know that the charge there needs to equal an overall -1 charge. We know we take oxygen here, as we're assigning it with a -2. That gives us a -6 overall charge there. That means the nitrogen must have a +5 charge so that the overall charge on that ion will be a -1. Now this is just a review. You've seen this before, but I just want to point out again what an oxidizing agent is. You know that this compound A is oxidized because it loses electrons. It's also called a reducing agent. It's losing electrons, okay? The compound B is being reduced because it's gaining electrons. It's also called an oxidizing agent. Oxidizing agents are electron acceptors. So how can we identify the oxidizing and reducing agents? Let's work through a problem. First, we need to assign the oxidation states. Okay, that's the very first thing we do. We know these are elements. They have oxidation states of 0. We know chlorine, each of the chlorine atoms has an oxidation state of -1, and there are 3 of them. So that's a charge of -3. That means aluminum must be +3. So there's our oxidation states. Now let's identify elements and molecules that are reduced, which one is reduced, and we can see that the, let me choose a different color to make this easier. The chlorine, each of the chlorine atoms is going from an oxidation state of 0 to an oxidation state of -1. They are gaining electrons, therefore they are being reduced. Each of those chlorine atoms are being reduced. This is also the oxidizing agent. This molecule, the Cl2 molecule, is the oxidizing agent. It's being reduced, so it's facilitating the oxidation of something else. Next, let's look at the element or molecule that is oxidized, the one that loses electrons. And that looks like it's going to be the aluminum. Aluminum, each aluminum atom is a 0 oxidation state here, and it is going to a each one is a +3 oxidation state over here. So it is losing electrons. It is also the reducing agent because it is facilitating the reduction of the chlorine. So hopefully that makes sense. If you understand first the oxidation states and then look at, just simply find what is reduced and what is oxidized, you should be able to then easily identify which one is the reducing agent and which one is the oxidizing agent. It helps to write it down sometimes and just think about what is reduced and what is oxidized. From there, you can then turn that into which one is the reducing agent and which one is the oxidizing agent. Here is an advanced idea. If you have other ideas, please feel free to explore those, research questions that you have on this. I look forward to seeing what you have in class, and we do have a worksheet on this, so that'll be kind of fun. You can practice some of these skills that you've just learned in the video. See you in class.